Now, what is a symmetry group? Usually there is a very good physical reason why you want some symmetry. So for example, you want to take an object and move it but not destroy it, not distort it. That wouldn't be a symmetry. That would just produce a different object. That means symmetry group is defined by what it preserves. And that was original way of defining it until it got very fancy in the end of 19th century. By killing a Cartan, it became a complicated subject of Diophantine conditions or lattices and God knows what. But the physical thing was always, I want to preserve something. In classical world, Euclidean rule, what you want to do is you want to preserve length. And by that we mean we have some way of measuring. So I take my meter and I bring it to your object and I dot the two and I get a length out of it. So we have a norm. In Euclidean space, we say that the length of the vector squared is just the sum of the components, xi. And if you want to stick Minkowski in here, you can put some other metric. But symmetric metric in Euclidean world is just Kronecker delta. So what we want is, we want to allow only transformations, only G's that preserve that. In particular, what it means is I want G of x squared to be the same as x. And if I do it only by rotation, not by translation, that's a group that's called OD in the number of components, orthogonal group in number of components, which says that I want x dotted with G transpose x times T transpose times x itself. Now these are transpose matrix. I want it to be the same thing as x transpose x, which means that this transformation has to satisfy that its transpose is its inverse. And that's the definition of orthogonal group. So that's what all these matrices have to satisfy. Its transpose is the inverse of the matrix. But if you write it in terms of Lie algebra, it becomes very nice. See, these generators, they're immutable. The only thing we do is we change by parameter how much it transforms. So if we substitute this form, it should be true for any phi, so it should be also for the small ones. You will find that this statement is the same as saying that the transpose of the matrix is a minus the matrix itself. In other words, you write x times 1 plus parameter, small parameter, t transpose time 1 plus the same transformation on this vector. And that gives me, the first terms give me x transpose x, the thing that I liked already. And the second terms, the cross terms, give me that f, this parameter, a parameters, going from 1 to n for some group that preserves length. I'll pick up this term here, t transpose, plus this term. And the whole thing is being sandwiched between x transpose, these are matrices, right, xt. And this is true for any phi. So my original statement is xdx. Right, I want it to be the same before and after. So these cancel. And it's true for any x and any phi. In other words, this matrix has to be antisymmetric. So now that simplifies the world very much. It says that all orthogonal transformations are just generated by antisymmetric matrices. So now we, for example, know how to compute the dimension of an orthogonal group with n parameters. So if you want to do SON, its generators, TAs, are linearly independent antisymmetric matrices. So for example, I can just write as a sum where each matrix is empty except for one entry. And the number of those entries is n minus 1 over 2. So the dimension of the group you obtain very easily and quickly if you understand what the Lie algebra is. But if you were just thinking of group elements, it's something infinite dimensional, you don't know what it is. So for example, SO2, which is rotation in the plane, has 2 times 1 divided by 2, so dimension equals 1. SO3, which is what you need to do hydrogen atom, is 3 times 2 divided by 2. It's n equals 3. So going to Lie algebra simplifies the world enormously.